Okay, calculus class, this is a section on related rates. Related rates often happen when you have a number of circumstances, variables that are changing. If you read the first problem, it says the area of a circle increases at a rate of 20 inches squared per minute. What rate is the radius increasing when the radius is 5 inches? You can tell that this is a derivative right here. It is a rate of change. So we have all sorts of derivatives that are happening. For example, if I ask this question, what is changing? Well, first of all, you know that the area is changing. You also know the radius is changing. And you also know that time is changing. As time goes by, the area and the radius are changing. And so therefore, we really have three different variables: area, radius, and time, A, R, and T, that we need to account for. And so that really presents a little bit of a challenge. Fortunately for us, we understand how to use implicit differentiation. This will allow us to solve related rate problems. This first one's pretty straightforward. This is the area of a circle increases at that rate. It wants to know what the rate of the radius is increasing when the radius is 5 inches. So, you just think about it. You have a circle that has a radius, and it says that the area is increasing. So this circle is getting bigger. It also says that the area is increasing at a rate of 20 inches squared. That's a derivative. So we know that A prime, our derivative, happens to be equal to 20. You might think that there's a few other variables here as well. There are. The radius is 5 inches. And it says at what rate is the radius increasing. So what I'm really trying to find out is at what rate is the radius increasing. I'm looking for r prime. We know that we have a formula for the area of a circle, namely that area is equal to pi times r squared. If we take the derivative with respect to time, time is what's changing all of this, of A, the derivative with respect to time of pi r squared, you notice that t is not the same as A or r squared. Therefore, we have a situation where we need to use implicit differentiation. The derivative of A is A prime. Derivative of pi r squared is 2 pi r prime. Now it's time to fill in the blanks. We know that A prime is 20. We know that r is 5, and we're solving for r prime. I fill in my blanks. 20 equals 2 pi times 5 times r prime. 20 is equal to 10 pi times r prime. Solve for r prime. Divide both sides by 10 pi. And we get r prime is equal to 2 over pi. That would be inches per minute. So, that's an example of solving a related rates problem. You can tell that there's a lot of things that are changing, and it's important that we keep our work neat, and that we look for different relationships that exist. We're going to do 4 examples of these. Next one is the volume of a ball increasing at a rate of 10 centimeters cubed per second. At what rate is the diameter increasing when the volume is 100 cubic centimeters? So I have a ball. This is volume, so this is a sphere. It's increasing. It's wondering about the diameter. So as you look, it says at what rate is the diameter increasing? So I'm looking for d prime. This is the volume of the ball. Is increasing at 10 cubic centimeters per second. So that means that b prime is equal to 10. I know the current volume is equal to 100. Let's see if that is of help to me at all. What is the volume of a sphere? The volume of a sphere is equal to 4 over 3 pi r cubed. Again, we have diameter changing, we have radius changing, we have volume changing, we have time changing. As you notice, I'm looking for the diameter. However, my equation has r. Therefore, I must substitute. I'm going to write a relationship for d. Diameter is equal to twice the radius. If I solve for r, I can divide by 2, and I get 1/2 d is equal to r. I'm going to take that, and I'm going to substitute it in, and I arrive at this equation. Volume is equal to 4 over 3 times pi 1 over 2 d to the third power. If I simplify that, volume is equal to 4 over 3 pi times 1 over 8 d to the third power. 4 over 24 pi d to the third power. In other words, volume is equal to pi over 6 d to the third power. So now I have a volume formula that is in terms of the diameter and not the radius. Again, we want to take the derivative with respect to time. The derivative with respect to time of v is v prime equals 3 times pi over 6 d squared d prime. Let's put in our pieces. V prime, earlier, we stated was 10. 10 equals pi over 2. I have a d prime. The question is, what is d squared? Do I have a current value for d? No, I do not. What to do, what to do, what to do? I don't have a current value for d, but I do have a current value for v. I know v is 100. If you take 100 and set it equal to pi over 6, d to the third, you can figure out what the current diameter is in this situation. Multiply by the reciprocal. 600 over pi equals d to the third. Cube root both sides. If we cube root both sides, we come up with, have it written down, 5.76. So again, I just cube root both sides. If you do that on a calculator, 5.76. So, as I continue to solve this problem, I have 10 equals pi over 2 times d prime times 5.76 quantity squared. Multiply by the reciprocal, we get 20 over pi equals d prime times 5.76 squared. Divide both sides by 5.76 squared. 20 over pi times 5.76 squared equals d prime. If you carry that action out on your calculator, we end up with 1.2, 1.92. 1.92 is equal to d prime. 1.92 centimeters per second, I believe, was our label as we started out. Yes, centimeters and seconds. Oh, sorry about that. Small mistake there. Per minute. Forget about that. We'll say seconds. That would make the problem a little bit more difficult. No need to do that at this point. That was hard enough. So, you can see sometimes you have to substitute for D. Sometimes you have to figure out some pieces. That's pretty involved. Try another example. An airplane is traveling east at 600 miles an hour. Another is traveling north at 750 miles an hour. If they left the airport at the same time, how fast is the rate of their distance apart increasing after 2 hours? Sounds challenging. One's traveling east at a rate of 600 miles per hour. One's traveling north at a rate of 750 miles per hour. So, if they're currently located at those spots, the question is, how fast is their distance apart? What is the rate? The rate of their distance apart. The rate of their distance apart is changing. It can be referred to as d prime. That's what we're looking for. I currently know e prime. The rate that it's traveling towards the east is 600. The rate at which it's traveling to the north is 750. Oops, sorry, 600. I don't know d prime. Do I know E? Do I know N? Do I know D? Do I know those current values? I do. It says it's been traveling for 2 hours. So at a time of 2 hours. Well, if it's traveling 600 miles an hour to the east, after 2 hours it would be 1,200 miles. If it's traveling 750 miles an hour to the north, after 2 hours it would be 1,500 miles. How would I figure out how far apart they are? Well, actually, I can use the Pythagorean theorem. That's going to serve as the foundation for this problem. Namely, that d squared is equal to n squared plus e squared. And if we use that Pythagorean theorem, we can figure out that the current distance apart is approximately 1,920.93. Well, if we're trying to solve for d prime, if I take the derivative of this equation, I should arrive at a d prime. If I take the derivative with respect to t, it appears that I will get derivative of d squared will be 2d d prime equals 2n n prime plus 2e e prime. So now I plug in all these values. 2 times 1,920.93, that's the current value of d. D prime we don't know. N, what is n? It says that the current n value is 1,500. 2 times 1,500. Whoop. Times n prime. N prime, the current rate is 750. You can see that from right here. Plus 2 times e. The current e value is 1,200. And e prime is 600. So you can see I have all those values. I simply multiply and add them all together and divide and solve for d prime, I come up with d prime is equal to 960.47 miles per hour. There you have it. Again, I didn't do all the scratch work. I'm kind of running out of room, but obviously you can see that you just combine these together and then divide by whatever 2 times 1,920.93 is. You come up with 960.47. All right, one last problem. Corn is being emptied onto a pile at a rate of 12 cubic feet per minute and is taking the shape of a cone. How fast is the height of the pile increasing when the pile is 6 feet high, has a base diameter of 8? Got this cone shape. It's 8 feet in diameter. It's currently 6 feet high. They're dumping corn on a rate of 12 cubic feet per minute. 12 cubic feet. Cubic is a three-dimensional term. That means that our volume prime is equal to 12. We don't know at what rate the height is increasing. It says, how fast is the height increasing? That's what we're trying to find. We don't really know the diameter rate. We don't know the radius rate. We do know the current diameter. Current diameter is 8. We do know the current height. It's 6. We do know the current radius. It is 4. We do have a formula. We know that the volume of a cone is equal to 1 over 3 pi r squared times the height. Well, if we're trying to solve for the height of the pile, the rate of the height of the pile, we have to have h in there. We can't have this r. You might say, well, Mr. Gantz, we currently know that r is 4. So is that really a problem? Well, if you notice, if we were to take the derivative of that, we would have to use the product rule. Product rule would get an r prime and an h prime. And those are both two unknowns, h prime and r prime. And we can't really figure them out. So we need to substitute for r or h and then go back and solve. Since we're trying to solve for h prime, let's get rid of our r and substitute something in for it in terms of h. Well, that's my height. That's my radius. So I know that my height divided by my radius is going to be at a constant ratio of, it is currently 6 over 4. Again, we want to solve for the radius. If I cross multiply, I get 4h is equal to 6r. Divide both sides by 6. I get 2 over 3 times h is equal to r. So I could take that and use it. 2/3 of h goes in for r squared. As I do that, I can write my new equation. Volume is equal to 1 over 3 pi r squared 2 over 3 h quantity squared times h. So the volume is equal to 1 over 3 pi 4 over 9 h to the third. We multiply that. We get volume is equal to 4 over 27 times pi times h to the third. There. Now we've got a volume formula written in terms of h. I want to take the derivative of that with respect to time. The derivative of v with respect to time is v prime. Derivative of 4 pi over 27 h to the third is 3 times 4 times pi over 27 times h squared times h prime. Do I know v prime? Yep, it's 12. I can simplify this a little bit. 3 and 27 will reduce to 1 over 9, so I got 4 pi over 9 times, do we know the current height? 6. 6 squared is 36 times h prime. Divide both sides by 36, we get 1/3 is equal to 4 pi over 9 times h prime. Multiply by the reciprocal. We get 9 over 12 pi is equal to h prime. I can simplify that. 3 over 4 pi is equal to h prime. What is my label? Over 4 pi. In this case, my label is, let's see, we're feet per minute. The height is changing at the rate of 3 over 4 pi feet per minute. There you go. There's a nice introduction to related rates. Good luck. I know they're challenging. We'll need some practice.